Hi folks, welcome to part 2 on this first lesson on optimization problems. So here we're going to look at another geometry problem, but one that occurs on the Cartesian plane. All right, so here they want us to find the dimensions of the largest possible rectangle by area. So right away I should be thinking area equals length times width as the thing I'm trying to optimize. And this can be inscribed in the region enclosed by, so let's read this carefully, the positive x-axis, the positive y-axis, and this function y equals e to the negative x. All right, and they tell us that one side lies on the x-axis, one side lies on the y-axis. So one of the things you'll realize is that when these questions have a geometric context, the best thing to do is to draw a diagram, okay, just so we can figure out how we're going to solve this. So let's see what this rectangle would look like. So I'm dealing with the positive axes, so I'll draw my Cartesian plane like this, okay. Okay, it tells me that one side lies on the x-axis and one side lies on the y-axis. So my rectangle will look something like this. But how high can it go? Well, that's going to come from the function y equals e to the negative x. So let's draw y equals e to the negative x. Of course, looks something like this because it's a decaying exponential function. So again, if I have, 1, 2, that means the rest of my rectangle is going to look like this. All right. So much easier to now figure out how this problem is going to work now that I've got a diagram that I can work with. All right. So I know I'm trying to optimize the area of this rectangle, so length times width. But as we saw in the salt shaker problem, we have a function given in terms of two variables. All right, so now our next step is to try to write this as a function of one variable. Okay, and the constraint here is that the height of this rectangle is going to be determined by the y values of this function, because I realize that whatever height I've got, it's going to be some point on this function y equals e to the negative x. Okay, so if I call this point or this x value, just call it x, the height of the rectangle is just going to be given by e to the negative x. Okay, so this is going to be my length because from 0 to x is just x, and this is going to be my width. Okay, and so now I can rewrite this function a equals L times W as a equals x times e to the negative x. All right, so one thing I notice is that this is already a function of one variable. Okay, so I'm done in terms of representing a in a way that I can work with. And now let's come up with our domain. Okay, well, clearly x has to be bigger than 0. All right, because you can't have a width of 0, so it's got to be something bigger than 0. And really, there's no end to what x could be. Since e to the negative x only approaches 0, this could be an extremely long rectangle, that has very little width. Okay, so here x can be anything greater than 0. So yet again, we're not working with a closed interval, so we're going to have to make sure we justify any maxima or minima. All right, but now we have what we wanted, a function representing our measure, in this case your area, given in terms of one variable, the x value on my Cartesian plane. All right, so let's go to the next step, which is to use our calculus tools. Okay, so this function is no issues with the derivative not existing, so I'm just going to look for where the derivative is equal to 0. So let's start by finding the derivative. So derivative of x is 1 times the second function, e to the negative x, plus x times the derivative of e to the negative x. So I'm going to have to use a chain rule here. So it's just going to be e to the negative x times the derivative of negative x, which is just negative 1. Okay, and I need to solve for when this is equal to 0. I see a common factor, so we've seen this type of thing many times before, so e to the negative x. And what are we left with here? We're just left with 1, and here we're going to be left with minus x. All right. This can never be equal to 0, so it means my only critical point is going to be x equals 1. Okay, but again, I'm looking for a maximum value. I need to justify that this indeed does give me a maximum value on my domain here. All right, so let's draw our number line, A prime. Again, I'm only interested in greater than 0. 1, so let's stick in, 0.5, so this is always positive. 1 minus 0.5, so it's going to be positive, whereas if I put in x equals 2, 1 minus 2 is negative. Okay, so that means we do have a max, and in fact, at least from 0 to infinity, well, if this is a maximum value, to the left, it's always increasing, and then to the right, it's always decreasing. I don't care how it decreases. I don't care if there's any points of inflection. I know that it's continually going to be decreasing. So this justifies the fact that in our domain, this is indeed an absolute max and not just a local one. All right, and so here, let me, now that I've figured out where my maximum occurs, let's go back and determine what they want, and what they want is the dimensions of this rectangle. Okay, so we have that the length is just given by the x value, as we said before, so it's just going to be 1 unit. Since we don't have any particular units, we'll just say 1 unit, and then the width, remember, is just given by e to the negative x, so e to the negative 1, e to the negative 1 units. Okay, or I guess more nicely if we put as 1 over e units. Okay, so if we want to maximize the area of a rectangle that's contained within this region, the x-axis, the y-axis, and the function y equals negative x, this is going to be the dimensions for that. So again, just to recap, what are we trying to optimize? Write it in terms of one variable with a domain, calculus methods to determine your optimal value, and then go back and make sure you're answering the question that's being posed in the particular problem. All right, that's it for this one.